Welcome back to Cloud 42. I'm James. If you have been following the channel, you'd no doubt recognize this setup. I have my function generator here to generate a sine wave. We're running that through this toroidal filter that's used on the output of a variable frequency drive to block noise, and running the output of that into an oscilloscope so we can measure the amplitude at different frequencies. Did a whole previous video on this, and we looked at how these cores worked, looked at some frequency response plots, and actually ran some tests with the oscilloscope to validate that. If you have not seen that video, there's a card up here in the corner of the screen, and there's a link down in the description. You can go check that out. We're not going to cover all of that ground today, but in one of the comments, somebody suggested using a white noise frequency source to get a broadband noise signal, run that through, and then plot it with a fast Fourier transform on the oscilloscope. I've played around with the tools that I have. I don't really have a white noise source. I tried to generate some broadband noise with a square wave, didn't really have a lot of luck. But there is another way to visualize the frequency response similar to a Bode plot or a Bode plot that I showed in the last video with an oscilloscope. And the way you do that is by using a sweep on the function generator to sweep through a range of frequencies, and then time the horizontal sweep on the oscilloscope to match that so you can see the frequency response across the frequencies. And I've been playing around with that. I thought it was kind of cool, so I thought I'd just do a quick follow-up video showing how that is done. So let me power up the function generator. And once again, this is an ancient piece of equipment. The fan generates quite a bit of noise. So let's start out with a 1 kilohertz sine wave at 1 volt RMS. And we've got that here on the oscilloscope, and you can just see the sine wave. Now, last time we went through and we ran this through a whole bunch of different frequencies manually and looked at the output response. But I want to set up the frequency sweep to do that instead. So I will set the start frequency to 10 hertz and the stop frequency to 10 megahertz. Now when I start this, what happens, you can see on the oscilloscope, let me see if I can expand this a little bit on the time base. So what's happening is this is sweeping up and down. So it goes all the way down to 10 hertz, sweeps up to 10 kilohertz, and sweeps back down over a time of 1 second by default. And the oscilloscope is just refreshing and catching it at various times along the way. What we would really like to do is have it sweep horizontally over the same time period that the function generator is sweeping across the frequencies, get that synchronized, and then we should be able to see the change in amplitude over time. So we need to scale the horizontal way out so that we can see that. Okay, I've got this way slowed down, so we're 1 second per horizontal division. And what you're seeing here is the spike at low frequency, because remember, at low frequency, the full signal amplitude is passed through the filter, and as the frequency goes up, the amplitude goes down because the filter is blocking the high frequencies. So we can see several cycles here, and I can pull this down so we see a couple. So what's happening is we're starting at low frequency, it's sweeping up to the highest frequency, and then sweeping back down, because that's how the sweep in this, the linear sweep in this function generator works, is by sweeping up and down and then up and down. I don't know how to get it to go in a sawtooth. I don't think it does that on the linear sweep. I only think that does that on the log. We'll get to that in a minute. So we need a way to synchronize this so that we can get it positioned horizontally. Now this synthesizer has what's called a vertical blanking output, and I have that hooked up to channel 4 here on the oscilloscope. So I can turn that on, and you can see on this separate trace, this signal is low while the frequency is sweeping up, and then it goes high when the frequency then is sweeping down. So we can use this as a trigger. If we trigger on the falling edge, we'll have our trigger point right at the bottom before it starts sweeping up. So I will switch my trigger source to channel 4. Oops. and I have it set to the negative slope, so you can see my trigger point is right here. I can scale this up so we can get to I just want to catch this one low frequency here. Scale that, and then I will move it horizontally so that that's over on the left-hand edge of the screen. Now I really want to just see the amplitude on this, so I can set my left hand, or set the center, the 0 point. This is actually, a sine wave going up and down, but it's just looking solid because of the slow scan. If I set this down to the bottom corner of the screen, select channel 1 first, bring that down to the bottom corner of the screen, and then turn up the vertical amplitude. Now I have what looks like a bode plot, where I have the amplitude at the highest point here, and then as the frequency sweeps up, it drops down. Now, one thing that's going on here right now is there are actually 12 divisions across here, and I have the sweep time set to 1 second. I don't have a way to get this to go to the right-hand side of the screen, but if I set the sweep to 1.2 seconds, I can get this ramp up to go the full width of the screen. So I'll just set the time to 1.2 seconds. And now we have the complete frequency response. And that was a start frequency of 10 hertz, a stop frequency of 10 megahertz. So this is what the frequency response of this coil looks like. Now if I take it out of circuit, just short across it here, you can see that we get a mostly flat frequency response. I honestly don't know what's causing this little peak here. Something is resonant at that frequency and the gain is higher or the loss is less. I don't know, maybe somebody who actually knows more about this stuff can chime in the comments and let me know why that is. But if we look at it with the coil in circuit, we can see that the low frequencies are passed and then the high frequencies are attenuated. Now this isn't ideal because the frequency domain across here is linear. And normally you would view something like this logarithmically. So the bode plots I showed before had a logarithmic scale. Well, this function generator has a logarithmic sweep mode, so I can just put this into log mode and it will sweep logarithmically. Now, because we set the start frequency to 10 hertz and the stop frequency to 10 megahertz, it means we have 6 orders of magnitude from the left to the right, which is really handy because we have 12 divisions. So if I grab a pencil here to point with, at the left-hand edge of the screen, this is 10 hertz. We go over 2 divisions, and this is 100 hertz, 1000 hertz, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz. So we have a nice, clean logarithmic scale that we can read off of the reticle here on the oscilloscope. And if you look at this, so you can see this is, 10, 100, 1 kilohertz, 10 kilohertz, 100 kilohertz. So right here, we've lost about half of the amplitude right at about 100 kilohertz. Now, ideally, you would have the Y also logarithmic, so you could read this off in decibels, and if we had a real spectrum analyzer, that's how we'd be reading it. But this gives you a good idea of what the amplitude looks like, and if you remember from the bode plots we looked at before, they looked very much like this. Let me turn off channel 4 so it's not in the way there. So you can see that same frequency response. I thought this was kind of cool because now we have this with a relatively inexpensive oscilloscope. This is what, a $350 to $500, depending on where you get it, oscilloscope, the Rigel DS1054. So this is the 50 megahertz version, and I've installed the codes to convert it to 100 megahertz. But still, it's a relatively inexpensive, entry-level, kind of 4-channel digital oscilloscope. And we can get a frequency response plot here by adding a function generator. These function generators, I mean, this is old tech, but these are available on eBay, not too expensive. And so this is a relatively inexpensive setup to be able to do this compared to a proper sweep generator or a spectrum analyzer. So the other thing that we did that I thought was kind of interesting is we played around with adding a capacitor for the filter. And in that last video, I put the capacitor on the generator side, so upstream of the coil. And I was told in the comments by a couple of different people that I would get a much better filtering effect if I put the capacitor after the coil. I don't know, maybe. Let's find out. So let's clip this in using the same way I had it clipped in before the coil. Now remember, we've lost about half the amplitude right here at about 100 kilohertz. So let's clip this in. Maybe. And let's see what we get. Okay, we'll let that settle out. Now the 50% point is now shifted a little bit to the left, and so we're at 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz. So now we've lost about half of that. So this is a logarithmic scale, so we have dropped that down. Let's see, if this was 100, and now we're back past 10, so what is that? 30 kilohertz. We've taken it from 100 kilohertz down to 30 kilohertz. And again, this is not a spectrum analyzer, so this is not the easiest way to read it. You know, this is not the best tool for this job. But you can see we've shifted the frequency considerably to the left, and you'll note that the residual amplitude down here at the higher frequencies is lower. So the total attenuation is lower, and the point at which that attenuation starts has shifted downward in the frequency. So just to be clear, let me disconnect it. And you see the amplitude jumps up and the frequency response moves to the right. And if I clip it back in, the high frequencies are attenuated much, much more, and that begins at a lower frequency. Let's try putting it after. So now I'm going to shift this to the other side so that this is after the coil, and see what we get. So in terms of the amplitude afterward, we get just about the same thing, and we're somewhere between 10 and 100 kilohertz for the halfway point here. So it really appears to me to make very little difference whether this is in before or after. I can switch back and forth between these. So this is the response with it clipped in before the coil, and this is the response with it clipped in after the coil. There's basically no difference. So again, I'm not an electronics engineer. I certainly don't have a degree in this stuff. So as a hobbyist, you know, this is good enough for me. I can kind of see the response. And I just thought this was sort of interesting to be able to visualize this with relatively inexpensive gear. In fact, the same gear that I was using to make you imagine what the curve looked like, turns out you can actually plot it out and see what the curves looks like. So I thought that was interesting, and I was having fun with it. I thought I'd make a video and share it. If you're enjoying these videos, give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.